what if there's no overlap? Okay, if we're talking about the domain of a combined function, the question is what if there's no overlap? If there's no overlap, then that means that resultant function will be undefined. Okay, there won't be any values for x that will work for those. Yeah, because if you plug a value for x in and it, like let's say it's out here, okay, for f of x, then it works for g of x but doesn't work for f of x. So how do you factor that into the combined function h of x? It doesn't. It's like an undefined value. Even if you add something to an undefined value, what's the result, right? So yeah, if there's no overlap, then yeah, it's undefined function. Okay. Now range is a bit different. Okay, the y values, you kind of right now just kind of have to graph it. If you want to see if there's more than one functions combined, you might have to just graph it and take your best guess at what's this range, what's this range. Same sort of idea, but you might have to look at the combined function. So it's not as straightforward as this always. Okay, so let's move on to our example here. So determine the sum of two functions. Okay, going to kind of move through this fairly quickly. Consider these two functions. F of x is 2x plus 1, and g of x is x squared. Determine the equation of h of x where it is the sum of the two. Okay, well, that's going to be pretty easy. All we do is we take 2x plus 1 and we add x squared. Good idea to write this in a sort of a standard form in a descending degree there. So x squared plus 2x plus 1. Okay, so you're just combining the two. That would be the equation. Sketching the graphs. All right. Obviously, we could, do some table of values, sketch the graphs, just like we did with the original example. Okay, which was up here. Okay, that's one method. Right. You could get the calculator to help you if you want to graph on the calculator, but you could do it pretty easily here. It might take a little bit more time, but you'd have some more exact values. But to sketch the graph, we could use the graphing calculator and sketch that. So let's just take a moment to do that. So we graph the first two first and graph those. This is what the combination is going to look like. Okay, now I'm zoomed in from another example. That doesn't look too bad. I'll just adjust that window. Okay, so there's the two. X squared is obviously that parabola, and 2x plus 1 is this straight line there. So let's graph h of x as well and see if we did this right. See if it makes sense graphically. Let's go down there, and we'll do x squared plus 2x plus 1. And we'll graph that as well. And it kind of looks like this. Now, just by looking at that, you might not be able to say, hey, that's right. But if we take a look at y values and we add them, then maybe we're in a better shape. So look at this right here. If we have x equals 1 right here, okay, for the first function, it's like maybe a half, right? Or no, that's 1, sorry. Yeah, 1 for x squared. 1 plus this one up here, okay, looks like about 3. And so we have 1 plus 3 should be 4, and there is y equals 4 on the third one. So you can kind of piece that, and of course you can use your calculator by doing second function trace, do a value, hit 1 there, and it'll show you on this one it's 3, on that one it's 1, so on the other one should be 4. Yep, 1 plus 3 is 4. Okay, so you can check it on your calculator. If we look at the domain and the range, okay, of h of x, that's the resultant function, you can just take a look at this function and, the domain, this is a parabola, so the domain is xer, all real values of x. The range, okay, again, we've graphed it, so you can go back to your graph and take a peek there. Okay, the range is obviously everything greater than or equal to 0. Okay, looking at that function right here. So there's your domain and range from the graph or just from using logic. And then determine the values of f of x, g of x, and h of x when x equals 4. We can do that algebraically or, like I said, on the graphing calculator. So I showed you an example of how to do that in the graphing calculator. So if we look at f of 4, that's 2 times 4 plus 1 is 9. G of 4 is 4 squared, so that's 16. And h of 4 is 4 squared plus 2 times 4 plus 1. And so that would be 16 plus 8 plus 1. And of course that's 25. So that all checks out. We have 9 plus 16 equals 25. Okay, I had one other example here I was going to go through with you. We don't do a whole lot of word problems. I assigned some word problems, but let's just go over one that would include, this is an application of why are we doing this sum and these operations of functions, right? This is an application. So in example 4, and you can find this in your textbook there, be on page 41, it says, Reach for the Top is an academic challenge program offered to students across Canada. Suppose the cost of t-shirts for the program includes a $125 fixed costs and $7.50 per t-shirt. The t-shirts are sold for $12 each. So A says, write an equation to represent the total cost as a function of the number n of t-shirts produced. Okay, so the cost as a function of n. You might write that in function notation as capital C, because it's cost, and it says right here use capital C, as a function of n, so bracket n, right? C of n. So we have $7.50 per t-shirt, so that's $7.50. You can put a dollar sign there to remind us of what that means. Per t-shirt, right? Times n. And then we know that there's always a $125 dollar fixed cost there. So 7.50 times n, or you can just do 7.5 n. That's fine as well. Okay. The revenue is how much money you get, right? So it's $12 per t-shirt. So we write a revenue function as a function of t-shirts. We're going to get $12, okay, per t-shirt. $12 each. So it says graph the total cost and revenue functions on the same set of axes. What does the point of intersection represent? Okay, so let's do that real quick. Again, graphing calculator helps us out quite a bit there. So let's clear everything off. And you can quickly do that. 7.5 n plus 125. And the second function would be 12n. Or x, obviously it's going to show up as x. Okay, so if we graph this and you don't see the intersection point, which that question is asking you about, then you'll have to adjust your window. So obviously I need more y, and I could use less x here. So I could use less x, so let's go 30, and I need a lot more y, so let's go 250. And see if that shows us the intersection point. Oh, missed it by that much. So y max, let's go 350. That should do it there. And we get an intersection point. Ooh, barely. Okay, but there it is. That'll work. It's on the screen, so that should work. So here's our two lines. You hit trace. You can see that's your. This is the cost, okay, of the t-shirts, and this is the revenue function. So what does the intersection point actually refer to? What does it represent? The intersection point. Anybody? It represents profit. Breaking even. Okay, you want to, what did you say? Oh, where you start to make profit. Okay. Yeah. I think that's better. Okay. This point, remember, think about the functions. That's where your cost and your revenue are the same. So the money you're putting in and the money you're getting back out is identical. So the intersection point over here is the break-even point. After that, now when you said after that, what you mean is when n is greater than the n value for this intersection point, that's when you're going to start to have a higher revenue than cost. Okay. That's fine. That's good. But I guess the reason why we're doing this chapter is instead of kind of thinking through that and using only these two functions, why don't we come up with a third function, called a profit function? That's the difference between the revenue and the cost. And so the reason why we're doing this chapter is to simplify stuff like this. So profit is going to be what? Profit is going to be how much we end up with in the long run, right? So it's going to be, which one's first? Revenue minus cost or cost minus revenue? Okay, revenue minus cost. Yeah, how much do you make? Take away the stuff that you owe or that you have to put in. And so the profit function is going to be 12n minus 7.5n minus 125. Because you have to subtract this whole thing, right? So it's minus this whole thing, so it's negative here. Sorry? Well, you don't have to put brackets. I did the two steps at once, right? So yeah, if you're going to use brackets, okay, then you can do 12n minus and then bracket 7.5n plus 125, right? Which turns out to be that. So I skipped a step there, sorry. But yes, brackets, and then that's what it ends up to be. So this is the, now one more step to combine, right? 12n minus 7.5n is going to be 4.5n, and of course that's $4.50 times the number of shirts minus 125. This is your profit function now. That's what you're going to make. So you can now graph this, and you can see what your profit's at. You can see how many shirts you have to sell in order to make a profit. You can also calculate your profit really quickly by just plugging in how many shirts you sold. Let's say on a day you sold 100 shirts. Well, your profit for 100 shirts sold would be $4.50 times 100 minus your input cost there, the fixed cost of 125, right? So that's going to be 450 minus 125. That's, what's that, 325? $325 that you made that day if you sold 100 shirts. That's your profit. That's taking into account all the money you made, and that's taking off all the money that you owe. Okay, so we didn't really do C and D exactly the way they asked, but I think we got the picture. We'll graph it real quick to show you what the function looks like. All right, so these are the three graphs right here, and you can see here this is your revenue, this is your cost, so there's your break-even point, and after this value, your profit starts to be in the plus now. Before that, if you only sold this many shirts, you would be in the hole. You wouldn't make enough compared to what you spent. Okay, you'd be owing money still. So that's why that this is zero, the profit is zero at the break-even point. And now this is your function of the profit. So here's a review of sort of the lesson here, what we've taken a look at. We can add two functions, f of x and g of x, to form a combined function, h of x. There's some notation that's new. You can also subtract the domains, whatever the domain is for the one and the other, wherever they overlap or wherever they're combined. Wherever they're combined, that's the function of the resultant, the domain of the resultant function. You have to look for the range on the graph maybe. You can sketch all three, and the y values for each x value should combine properly. Okay?